Hey everyone, today's video will be on the cosine rule. Now for a bit of context, as we probably covered in class already, in trig, you usually deal with right triangles because that's what trig was defined for. All of the trig ratios, sine, cos, tan, only work for right triangles. So you have an angle, theta, the opposite, the adjacent, the hypotenuse. Sine would be opposite over hypotenuse. Tan would be opposite over adjacent. And cos would be adjacent over hypotenuse. So as you can see, it's quite it's pretty limited. But then we learn about these rules that work for non-right triangles. And last week we learned about sine rule. And what sine rule says is that the ratio of opposite sides of a side and sine of the opposite angle is the same or constant for all sides. So for example, if you have a triangle like this, say we know this is 5, this is 6, and this is 8, and I'm not going to label these angles. Okay, I'm going to label these angles arbitrarily. Now, this example that I've come up with is probably wrong because coming up with a triangle from scratch is very hard because sine and cos and tan don't give nice numbers. So this is definitely going to be wrong. But if I'm saying if this was a true triangle, as a result, I'm just going to call these theta, alpha and beta. The reason I'm calling them that is because knowing the exact angle is very hard. So what this theorem says is this: 5 over sine of, I'm just going to do ABC. 5 over sine of the opposite angle. What's opposite 5? It's B. Sine of B equals 6 over sine of the opposite angle, which is C, equals 8 over sine A. And that is the sine rule. Now cosine rule is actually a slightly different rule. And let's get into it now. This is another rule that also works for non-right triangles. But before I tell you the rule, let's motivate this. Say we have a problem like this: 5, 8, and this angle's 72 degrees. Now we're told to find I'm just trying to make it less of a, let's go back to what we had. Okay, so we're trying to make, this is 72 degrees here. We're told to find x. Now our first thought should be, well, it's non-right triangle, so we should try to use sine rule. What happens if we try to use sine rule? What do we have? We have x, and the opposite angle is 72. X over sine 72 equals 8 over, I don't know, this, let's call this A, is 8 over sine A equals, this angle is unknown, but I think you can use the fact that these all add up to 180 to get this is 108 minus A, equals 5 over sine 108 minus A. Now, none of these equations we can solve. We don't know what this is because the x is unknown. We don't know what these are because the a is unknown. So we can't solve. We're stuck. Okay, so that means we can't do this approach. So let's actually go back to the basics. Let's use a knowledge of right triangles and construct the right triangles we need. Maybe this line. Now, as you've probably seen from like the derivation and the constructions and the sine rule problems, you probably shouldn't cut the 72-degree angle. So you really don't want to draw this line. If you draw this line, you cut the 72 and you don't know what happens to it. So ideally, you probably want to cut this one or this one. Actually, I think this one might be nicer. Okay. Still not super nice. We have we have a right triangle now. Okay, what can we do with it? It doesn't seem very clear what the path is. But we know these two sides, let's call this x, and this add up to 5. This is 5 minus x. And notice how we have one side and one angle in this right triangle. That would mean that we can find this x using a trig. In particular, relative to this angle, x is the adjacent side and 8 is the hypotenuse because it's opposite the right angle. So if you use cos of 72, you get x over 8. That would mean x is 8 cos 72. Now, if we were to solve this, we'll get that this is equal to 8 cos 72. Let me quickly solve this. This is equal to 2.43. Sorry, 2.4721. This is 2.74721. Then we can get this is 5 minus 2.4721. So 5 minus x is 5 minus 2.4721. Okay, well that seems pretty good. It's 2.5 something, 5279, let's say, approximately. What's okay? So 2.5279. Well, our goal is to find x. We have only one side. We don't know anything else. Oh, but wait, look. This side is another part of this triangle, and it's also common. This side's common to both triangles. So we can use this 72-degree triangle, right triangle, to find this side as well. And it'll be sine 72. So it'll be x8 sine 72. If you solve for this, you'll get it 7.61. Again, I rushed this step here, but it's basic trig. You should do this and figure this out. This is 7.61. And then now you have two sides of a right triangle. So how can we find x? Well, you use Pythag. So it will be approximately 64. It'll be x squared will be about 64.28. That means x is basically 8. Yeah, x is 8.02. So you can say x is 8, about 8 as well. Now that works, but again, very annoying and long construction. Is there a shortcut? Remember, with similar problems with sine rule, was there a shortcut we could use? And yes, there absolutely is. It's the cosine rule now. And this says that if we know in any triangle, if we know AB and the angle between it, let's call it big C, and then let's say the opposite side is unknown, little c is unknown, you can find C using this formula. C squared equals A squared plus B squared. Ooh, whoa, that looks very much like Pythag. And it is indeed a generalization of Pythag. This is the formula, the general Pythag formula that works for all triangles, because Pythag only works for right triangles. And now with this formula, this question becomes super easy. What do we have? 5, 8, 72. That means A is 5, B is 8, and C is 72, the big C. And then if we want to find little c, which is the unknown, or x here, little c is x, so we can just call it x. X squared is 5 squared plus 8 squared minus 2 times 5 times 8 times cos 72, which is 89 minus 80 cos 72. And if you were to solve this, you'll get that this is equal to 64.2728. That's the exact same answer we had before. When we square root it, it'll be 8.02 again. And actually, 64.28 is probably the more accurate answer, because we carried answers here. We carried our 2.52 and 7.61. They're not exact values. And so you get the even more accurate answer when you do cosine rule. So why should we do cosine rule instead of this construction? Well, it's just easier. Now, of course, the ideas behind the construction are super important, and these ideas are what led to the cosine rule. But I think it's important to realize how much faster it is once you learn it, and also how much more accurate you can be, because you don't need to worry about carrying lots of values around. That's the cosine rule. Now let's do the proof of the cosine rule. It's basically the exact same process as this question. So you just do it with general numbers. Let's say we know A, B, and C. So we know A, let's do it in good colors. A, B, and C are known. Big C. We don't know little c. So our goal is to find C. So what can we do? Well, we do basically the same thing as before. Draw a right triangle. Then we go, well, since we pretend we know the values, again, this is for the proof, so you pretend you know the unknowns. And you go, well, you do the same thing as before. And if you do the same thing, you'll get that, call this A, B, C. Let's call this H. The CH equals, get that cos C equals CH over AC, which means CH is AC cos, but AC is just A, so let's call it B, sorry, not A, B. CH is B cos C. This is B cos C. That would mean this one is A minus B cos C, because they should add up to A. And then you can find this similarly as B sine C by using Pythag, just like you did to find B cos C. And then you just, sorry, not by Pythag, you find this by Trig. Trig adds to A. This is the reasons why we get these values. And then how do we find the unknown AB, which is C? Well, we use Pythag. C squared equals BH squared plus AH squared. BH squared is B sine C squared. AH squared is A minus B cos C squared. If you expand this, you get B squared sine C whole thing squared plus A squared. Ooh, before you do this, be cautious of this expansion. A lot of people think this is just A squared plus B squared cos C of the whole thing squared. It's not. You have to square this with the proper distributive property. And if you do the expansion, you get A squared minus 2AB cos C plus B squared cos C the whole thing squared. And here's the trick. Special identity you're going to learn, that we'll learn now. This special identity says that cos C squared plus sine C squared equals 1 for every single angle. Actually, let me just make it not C, so C is a known angle. So any angle, call it x. Cos x squared plus sine x squared equals 1 for all x. Sorry, this symbol means for all. For all, this is the symbol, it's a little upside down A. For all x. Why is this true? You can see here that, here's the proof why this is true. Well, this is the same angle, right? So they're on the same triangle. So within the same triangle, we have, this is opposite over hypotenuse, sorry, adjacent over hypotenuse, my bad, squared, and this is opposite over hypotenuse squared. And this is a triangle, so it's opposite, adjacent, hypotenuse. And notice how this is just a squared on h squared plus o squared on h squared. And as we know, a squared plus o squared by Pythag will be h squared. This is h squared over h squared, which is just 1. And that's why this theorem is true. Notice how these two angles are the same. So this only works if you have like cos 20 squared plus sine 20, the whole thing squared, of course. If this was 30, it won't work. So what's the takeaway? Takeaway is that we have, now how can we use this identity? Well, we're going to use it like this. Bring this b squared sine c squared plus b squared cos c squared plus a squared minus 2ab cos c, which is just b squared times by sine squared, notice how these two things up to 1, so you just have really 1b squared. This becomes b squared, and you have plus a squared minus 2ab cos c. And that's exactly the rule you want. It's just the same rule except with the b squared and a squared swapped around, but they're equal. That's the proof of the cosine rule. That's it for today's video, everyone. We went over cosine rule. Please go over this. This is a very important concept. But yeah, see you next time. Bye.